Hello, everyone, and welcome back. And thank you very much for joining us in today's Jconnect webinar. My name is Kevin Cowell, Business Development Specialist from JETRO Chicago, and I will be moderating today's webinar. Our topic for today is Battery Advanced Materials, featuring two spinouts from Northwestern University, Nanograph and Alexion, and two companies housed in the Battery Innovation Center outside of Bloomington, Indiana, Ateos and Brightvolt. Today's webinar will feature a look at intriguing innovations in battery chemistry and material science, which are aiming to improve energy density, reliability, size, and more. Demand for battery innovations has grown dramatically with the global push for electrification of vehicles and transportation, as well as the soaring growth in consumer electronics and wearables. We hope to help connect our innovative speakers to you after this program. And if this is your first time attending the Jconnect webinar, we would like to welcome you. Our focus is to help connect innovative North American startups to Japanese affiliated companies doing business here in North America, and most importantly, to facilitate business relationships between the two. Likewise, it helps to aim to improve the productivity of Japanese companies and to help accelerate their open innovation strategies. I'd also like to remind you again to check out the landing page for the Jconnect Webinar Series on the JETRO USA webpage. You can find dates and information on upcoming industry topics, as well as recordings of our previous webinars. Today's webinar recording should be available on the website within 2 to 3 business days. So again, please check out JETRO USA's website for more information. I would like to now share a few housekeeping notes prior to beginning the webinar. First, we are switching today's format to direct questions individually to each speaker after their presentation concludes. Therefore, we will not have the group panel session with questions and answers as we have had in the previous Jconnect webinars. We kindly appreciate your questions for the speakers about their technology and their company, and we welcome any feedback about the agenda format change after the event. Here's how to operate the control panel for questions. Your microphones are muted to avoid noises. For this reason, questions should be entered in the box labeled question in the control panel on the far right side of the screen. If you don't see the panel, click on the orange arrow to show the panel. Questions will be answered after each presentation has concluded. In the unlikely event that the webinar system shuts down for any reason, we will reboot the system for you. Please log in a few minutes after that using the Join the Webinar button. Today's talk will be recorded and the video will be made in a few days on the JETRO USA website, as I mentioned. In addition, you will be asked to complete a quick questionnaire after the webinar. So I would now like to introduce our first speaker from Nanograph, Dr. Chip Breitenkamp. Nanograph is an advanced materials company developing silicone graphene materials for the next generation of lithium-ion batteries, enabling increased battery energy and power density, all while being produced via a low-cost solution chemistry-based manufacturing process. Chip Breitenkamp leads business development and marketing from Nanograph and manages partnership efforts with customers and manufacturers. He previously co-founded and served as CTO of Enzyme Technologies, a biotech company focused on the development of advanced polymer nanoparticles for targeted drug delivery. As a researcher, Chip is listed as an inventor on 20 patent families that represent 28 issued US and international patents and 18 peer-reviewed publications. He received a PhD in polymer science and engineering from the University of Massachusetts Amherst and a BS in polymer science from the University of Southern Mississippi. Chip, it's good to see you.
Yeah, thank you, Kevin. Can you hear me?
We can hear you loud and clear, so I'll go ahead and hand things over to you and we'll let you start with the first presentation. So welcome.
Yeah, thank you for the opportunity to be here. It's always great to participate in these things and share a little bit about what we're doing. As you mentioned, we are a Northwestern spinout based in Chicago. We've been around for about 8 years and really are hitting a pretty impressive inflection point right now in terms of manufacturing scale up, in terms of what we've been able to do in commercial cells already. And so I'm excited to tell you a little bit about that today. Sorry, there we go. Yeah, and since I'm the first speaker, I get to be the one to give some of the intro here. I think everyone is excited about the prospects of electrification. You know, certainly Uh, when we're talking about electric vehicles, that's been around for a long time in Asia, and now we're starting to see that tsunami of demand across to Europe and now to the US. And with electrification and sort of growing this new green economy, batteries and the battery cell in particular could not be more important. And as you mentioned earlier, driving energy density is one of the biggest limiting factors in terms of cell chemistry and transforming a lot of things like solar, wind, all of these various things into a reality. And silicon, we believe to be the most important driver of energy density in cells over the next 10 years. And while maybe a few years ago silicon seemed to be a little bit far out, I would say that's really changed since about 2016. Panasonic's been putting a small amount of silicon in every Tesla cell for the past 5 years. And what we've observed is, all of the major tier 1 battery manufacturers have now started, they've started to adopt silicon in small percentages to increase the energy density, even in electric vehicles. And so I'll tell you a little bit about our technology today, what we believe to be a best-in-class material that, again, we differentiate ourselves not only on performance, but by the fact that we've really designed the material to be low cost through the manufacturing processes that we're using. And these are manufacturing processes that we're scaling up, will be scaling up in Chicago. Let's talk a little bit about silicon here, because again, and if you put it in the context of a standard 18650 cell, which is one of the oldest sort of commercially relevant form factors, what we've been able to do over the past few decades is really improve energy density through first, design advances in the cell. And then I'd say, during the 2000s really it was the cathode's time to shine, really able to, increase energy density through cathode material advances. What we've seen over the last, like I said, 5 years is we believe it's really the anode's time to shine. And we believe that silicon is going to be the way to improve energy density. And what we've been able to do already just this year is push that threshold of the 18650 energy density up to 800 watt hours per liter by blending our silicon material with the traditional graphite materials. And as we say, if you take a look in the context of history, that's really a decade's worth of energy density improvements, which we think is pretty impressive. And I think everyone sort of understands that this is a pretty big growing market, depending on the numbers that you're looking at. The overall lithium-ion battery supply chain could be somewhere, $300 to $500 billion by 2030. Of that, active materials is a pretty sizable chunk. And of course, that includes cathodes, anodes, and everything else. That's estimated to be somewhere around $25 billion of the market. And what we've been able to determine is that's probably going to translate into over a $10 billion market just for silicon alone, if you sort of look at the projected amount needed to meet the battery cell needs over the next 10 years. So huge market, and obviously it's a very powerful technology for increasing energy density. And just to kind of set the stage for talking about our technology specifically, we always like to talk about other technologies that I'm sure that everyone has heard of at this point. As I mentioned, Panasonic's been putting a small amount of first generation carbon-coated silicon oxide in cells for 5 years now. It's very much a commercial product, produced at thousands of tons per year at a fairly low cost. If you look at the roadmap, certainly there's other companies that are pursuing, what we call pure silicon strategies. These aren't silicon oxide, and of course, solid state batteries, which has gotten a lot of attention over the past, I'd say, year or so. With QuantumScape and Solid Power, many of these other companies sort of coming out of stealth mode. We still believe that there are lots of improvements to make to silicon oxide, and that's really what we focused on, is try to take a commercial product that's fairly low risk and eliminate the pain points in that material and create something that's going to be the material for the next 10 years. A low risk material that, again, great performance, low cost. And it's really a contrast, I think, to a lot of these other technologies that, I'd say are still either at lab scale or certainly hasn't been proven out at EV scale yet. So what is our technology? Again, comparing it to the first generation carbon-coated silicon oxide, which had great capacity and has already achieved EV market adoption because of, again, cost and scale. What we've been able to do is use a metal doping process to eliminate the previous pain points with carbon-coated silicon oxide. And those would be, again, really low first cycle efficiencies, which were anywhere between 72, 74, 75%, and also the real swelling problem with silicon oxide as well, which as some of you may know, as it charges and discharges, it swells, it cracks, leads to electrical disconnection, and really leads to poor cycling. So what we've been able to do is develop a unique process to where we could dope the core of the material with lithium homogeneously. And again, our real expertise is in surface coatings, and we've developed a number of special coatings that complement this dope technology so that, again, we can achieve the same capacity that has always been there with silicon oxide, but we've improved the FCE up to 90%, still using that pathway, that manufacturing pathway that we already know has been scaled, and a cost pathway that we know it's going to be attractive for EV OEMs. And unlike pure silicon and solid state batteries, it's a technology that's ready now. Again, there's a lot of data here, but this is just a demonstration of what we've been able to do with our material in a standard 18650 cell. As we say, we believe we've made what still is the most powerful 18650 cell with our technology. That was a cell that was about a 3 amp hour capacity that could safely discharge at 30 amps. And that was a cell that was really geared towards power tool makers. Looking at some of the other competitors, tier 1 competitors, we're able to achieve that incredible capacity and discharge rate through the combination of the core and surface technologies that we use. And I think what we're most proud of, and I think there'll be a press release here in the next few weeks about this achievement, is the fact that we've been able to make the longest running 18650 cell, or the most energy dense 18650 cell. It's a 3.8 amp hour energy cell. Again, if you take a look at state-of-the-art cells from Panasonic and even LG Chem, the highest that's really achievable right now is 3.5 amp hours. And so we've been able to demonstrate just in one shot a 11 to 12% increase in nominal capacity. We've been able to achieve that 800 watt hour per liter energy density threshold as well. And again, this is with a material that very similar to what has already been commercialized, but just solves all of those technological pain points. And 11 to 12% energy density, may not mean a lot to lay people. And so we also like to give these little anecdotes of what that type of energy density means for real world performance. So the easiest way to do this is if you take a Tesla Model S. It uses an 18650 cell made by Panasonic, as many of you may know. If you replace all of those Panasonic 18650 cells with these improved energy density cells that we've just made, that would result in about a 28% in driving range. So as you can imagine, that's a really tangible difference to someone who's really has range anxiety with their electric vehicle. And it's certainly a way for EV OEMs to differentiate, based on their battery performance. So again, yeah, just as sort of a recap of the materials, what we've been able to do is, retain the high capacity of silicon oxide through this doping process, reduce first cycle losses, so first cycle efficiency of around 90%. And again, we've developed a number of special proprietary coatings that improve the processability of the material and the cycle life of the material. And again, we've already scaled this material capability up to 10 tons with our partner in Japan, JNC. And obviously we'll be further scaling that this year as well. And I think the way we try to differentiate the technology is that we are a true drop-in solution. This can be blended with graphite in a traditional slurry, coated, calendared, no changes to the manufacturing process at all. And we're doing this all with a material that we believe will achieve the same cost or lower cost as first generation silicon oxide at scale. And again, just a comparison here, the way we do this, just taking a look at the manufacturing process, newer, generation 2 silicon oxide technologies are using what we call a two-step process where, silicon oxide is first CVD coated and then doped after the fact. And this generates a process that's much higher cost than what's observed with first generation silicon oxide. It also leads to a material that isn't doped homogeneously throughout the core. And that has long-term effects on things like cycle life and just general performance of the material. And what we've been able to do is basically use a one-step synthesis where the doping process happens while the material is being made. We've developed a low-cost carbon coating, and again, with this process, we're looking at anywhere to between 30 and 40% reduction in cost. And of course, that's great news for EV makers who are obviously trying to push costs of batteries down, but retain that really great performance. And I've mentioned this already, our value proposition really isn't to replace graphite. It's a complement to graphite. And so we've been able, thus far, even in commercial cells, to blend all the way up to 20%. And, obviously we have prototypes and we have efforts to push that even higher. The material itself, compatible with all conventional cathode technologies. And, I think it's really important to understand the power of being able to use manufacturing processes that are low cost. So obviously today we've been able to show that 11% increase in energy density, and small scale will obviously have a huge impact on cell cost. Next year we'll be up to 36 tons, and you'll see that cell cost drop just to about a 7% increase over what's available today. And then at 1,000 tons, which we are aiming for 2024, we believe that we can push energy densities to at least 20%, maybe higher, while basically getting cost parity with graphite. Only very, very small differences in the cost of an 18650 cell. So again, I think this is a major differentiator for us, and why we are really hyper focused on scaling and being able to capture these cost advantages. We've had a lot of support along the way. I mean, obviously this is JETRO, and so we've had many many partnerships with Japanese companies along the way, none of them more important than JNC, who we partnered with in 2018 to help not only expand our footprint in Japan and Asia, but also as a manufacturing partner. They've helped us get to that 10-ton scale. Obviously, we've also had a lot of support from USABC, which is a conglomerate of the big 3 automakers. They've supported a lot of our work targeted towards electric vehicles. And then most recently, we've been really lucky to partner with the Department of Defense, who is going to be supporting this recent 18650 build. Our goal is to have these high energy density 18650s in the field by use with use from U.S. soldiers in the next 12 to 18 months. That's our goal. And obviously, the military is super interested in these because soldiers, when they go out on the battlefield, carry somewhere around 20 to 25 pounds of just batteries. So being able to increase the energy density is a huge advantage in terms of weight and also runtime as these electronics that they're using become even more sophisticated. So just want to point out some of the customer traction there. And then, yeah, I just want to thank everyone, for their time today. We have a great leadership team. Francis, our CEO, just done an amazing job getting us to this point. Dr. In Kim, who's a relatively recent addition to our team who came over from Samsung SDI, is really helping us translate this material into cells and commercially available cells and helping us scale up those processes as well. So I think with that, I think my time is up. And so just summarize, yeah, we are making a proprietary silicon anode material. We've already been able to demonstrate, that it works incredibly well in both power and energy cells. And I said our most recent achievement is the most energy dense 18650 that's been made. Our partners right now are really focused on power tools, U.S. military, and then also, with lots of partnerships with EV OEMs that will hopefully come to maturation in the 2023, 2024 time range. And so we're also raising money right now. If that's interest to anyone, we're trying to raise $15 to $20 million in our round B to further scale up this material. So thank you, Kevin. With that, I'll take any questions.
Thank you so much, Chip. Excellent presentation. I've got a couple questions coming in, and I'll start with one that I received in the registrations. One of the reasons I wanted you to go first with Nanograph is your partnership with JNC in Japan, which is obviously an outcome we'd like to see in similar fashion with our other speakers too. But what key characteristics do you look for in commercialization partners? And do you see a trend with this in the battery space with more collaboration and more partnerships?
Yeah, absolutely. I mean, every day you look, there's a joint venture, between some sort of OEM and some sort of material or cell maker. I'd say for us, and really just sort of, our specific case with JNC, when we partnered with them, we had a great technology at lab scale. What JNC brought was, not only manufacturing infrastructure, but over 100 years of scale-up experience. And it was a completely new material. It hadn't been scaled, and I think this is something that JNC and in particular, Japanese companies do very, very well is to take something that's pretty good and really perfect it and really help us scale. And that's just a capability we didn't have, and something that was, I'd say, one of the most important things to happen to us is to be able to say, yeah, we've de-risked this at least at a pilot scale at 10 tons per year.
And on a related question, obviously the public sector is another opportunity for partnership. Does Nanograph work with scientists at Argonne National Labs?
Yeah, so the history of Nanograph is not just associated with Northwestern. Some of those technologies were actually developed at Argonne as well, and we keep close partnerships with sort of all the academic groups, I would say, in Chicago, including Argonne. And in fact, I think we have our senior VP is having discussions with them in terms of trying to cooperate on things like cell builds and utilizing the infrastructure that's already there that would be very expensive for us to acquire. But how do we do our development work, and how do we utilize those government resources already there? So yeah, it's absolutely been very important to us, and we utilize them every day, just about, whether it be University of Chicago or Northwestern, Argonne, all of them.
And along with that, it looks like a question: have you worked with Dr. Goodahoe at University of Texas, Austin?
Not to my knowledge. I mean, that might be a good question for our technical team. I'm sure we're familiar, but certainly if someone wants to make an introduction, we'll always love to meet new people and figure out how we can work together.
And I know you kind of touched on this in your presentation, but what is your expected growth over maybe 1 to 3 years, 1 to 5 years, however you would like to answer that, and then the level of dependency on the global supply chain?
Yeah, so growth is everything for us right now. I think in many ways, like I showed, we've developed this technology. We've been able to show really what is a de-risking event in an 18650 cell. We've taken a commercially relevant cell, something we can hand to someone and have them test and say, hey, look, this works. And now for us, it's really about scale. And in some ways, it's a great time for us to try to get to that next step of 35 to 50 tons here in the US to be able to support the military. But I think the bigger goal for us is to get to that multi-thousand ton scale. And we've shown through cost modeling, that's where we become we get cost parity with graphite. The economics work well, our margins are better. And it's a great time to be doing that. I think everyone is really taking a close look at the global supply chain for batteries, and really trying to make sure that supply is going to meet demand. So I hope that answers your question. But yeah, I mean, growth is everything for us right now. We're hyper focused on, again, first scaling to around 50 tons, and then getting to that multi-thousand ton scale in the next, I'd say, 3 to 4 years.
Yeah, the kind of final question, kind of goes with that. What were the challenges towards scaling your technology? That you kind of touched upon it. Just if you want to add anything else, though.
Well, I think, there's certainly the technical challenge that always comes, when you're first trying to scale something. I think, what JNC's helped us do is really optimize our manufacturing process to we feel confident kind of moving forward. Financing is one of those things, and also, trying to also figure out where to do this. There's a huge supply chain in Asia. There's a growing supply chain in Europe and in the US. We're trying to find a way to sort of be able to address all of those and make the right choices in terms of where to scale and how to how to divvy that up, if you will, to maximize our opportunities everywhere.
Yeah, there's a lot of demand to bring it back home here to the US as well, I think. So hopefully, perhaps you can do that too at some point. So thank you so much for your presentation. And if you would like to give any final comment, now would be a good time.
No, I just, again, thank you for the opportunity to be here. And, Japan has been an incredibly important part of our success. And so we're always happy to be here and learn more. So thank you.
Thank you so much. And I almost forgot to launch a poll here. So we're going to go ahead and go to our next speaker here, Damien Despinois. He is the CEO of Alexion. Alexion is a startup that began with research based at Northwestern University and also scaled up at the Chain Reaction Innovations Accelerator at Argonne National Laboratory. Alexion has developed a drop-in graphene coating for lithium battery cathode materials that has driven a 35% increase in energy density and 30% battery cost reduction. Damien is the Chief Executive Officer of Alexion Inc. and is responsible for driving the business development, commercial, and strategic planning activities of the company. Damien has 15 plus years of leadership experience in the materials, energy, and industrial sectors with expertise in management consulting, technology commercialization and venture capital, chemical operations, and capital projects. Damien received his MBA from INSEAD, his MS of Chemical Engineering from IFP School, and his MS in Chemistry from Chimie Paris Tech. Damien, I'll go ahead and turn it over to you. I hope my French was okay for you.
Thank you. And can you see my screen as well?
Yes, of course.
Wonderful.
So okay, it's all yours.
Wonderful. Well, thank you for the introduction. And yes, your French was perfect. Better than my Japanese for sure. Good afternoon, everyone, and thank you for the opportunity. Since Chip, my colleague from Nanograph, talked at length about the prospect of the lithium-ion battery market, I'm going to skip that part. There's a point where I do sometimes disagree with him, but that's the nature of our business, is when he said that the time of the cathode was behind us in the 2012 to 2016 timeframe. I do disagree with that because the cathode is the highest cost component of a lithium-ion battery. It's 20% of the cell cost. It's also the largest driver and limiting factor of battery capacity. And however, when you look at the innovation in the battery space, component by component, you have a lot of innovation on electrolyte and particularly solid state. That's a recent trend. Anode has been an area of focus recently. Design and manufacturing has also seen a lot of innovation, but cathode, which is that highly expensive and highly limiting component, sees the stage battery deals. And that's where Alexion is focused, which positions ourselves into a high potential market, which is also an innovation white space. Our technology comes out of Northwestern University, so we are a sister company to Nanograph, and we are very friendly with them. And the core of our technology is a conformal, pristine graphene coating that's applied to cathode materials. On the left-hand side of my page, here what you see is the traditional approach of assembling lithium-ion battery cathodes, where the active particle, the large gray spheres on this schematic, are mixed together with little teeny beads of carbon black, which are the small black spheres, and this mix swims in the liquid, which is the electrolyte, which ensures the ionic conductivity between both sides of the battery. And this traditional design, which is the one that you encounter in cell phones, specialty applications, and or EV batteries, leaves very large of the cathode particle exposed to the electrolyte, which is an oxidizing environment, particularly at high charge rates. So that leaves very large surface of the cathode particle exposed to the electrolyte, where the electrolyte compounds can have access to the surface, degrade themselves, and degrade the material at the same time. So that leads to accelerated aging and also to the formation potentially of hotspots due to the point-to-point contact nature of the carbon black. On the right-hand side is how Alexion does things differently. We apply our pristine conformal graphene coating to commercially available cathode particle, and we essentially shrink wraps around the cathode particles a few layered graphene layer that allows the lithium to flow in and out of the coating, which is a desired property for our application, but blocks everything else from having access to the cathode particle surface, which leads to the suppression of degradation and hotspots. And also, graphene is one of the most conductive materials ever discovered, which is a desired property for lithium-ion batteries. As I was saying, the technology was invented at Northwestern University by Professor Hersam, who's a highly regarded scholar. He's a MacArthur Fellow, he's a repeat entrepreneur, and he's our Chief Scientific Officer. Technology was scaled up to pilot scale at Argonne National Lab by our Chief Technology Officer, Dr. Seo, over the past 2 years, and we are now at pre-pilot scale. And we just finished raising our seed round, which will allow us to get to the next level. And I've been with the company for a year, and my expertise is in commercialization and industrialization of new technologies, particularly chemicals. So after this segue, what I wanted to talk to you about is the performance improvement that we observe when we apply our technology to commercially available cathode particles. And what we see with our technology is a comprehensive performance improvement of the cathode material and the battery without trade-offs. So we jointly improve the cycle life and the stability of the material, the ability to operate at higher voltage and hence packing more energy in an existing battery, and also the ability to drive higher power density and particularly in low temperature applications. So what we've observed at the scale we're at is the ability to double the cycle life, packing 15% more energy density by increasing the operating voltage, getting 5 to 10 times more rate capability, which is a power property that's desired for specialty applications in particular. And also by encapsulating the cathode material in this graphene cage, we also increase the high temperature stability, and we mitigate the runaway reactions that release oxygen and lead to catastrophic failures of lithium-ion batteries. So that's what we observe with existing commercial material. But one value that's of high interest for the industry right now of our technology is to enable the next generation of cathode materials, which are very high in nickel and low in cobalt, which drives both a very high energy density, but also creates a lack of stability in the crystalline structure of the cathode material. And hence these materials, such as lithium nickel oxide, for example, need a stabilizing solution such as our conformal graphene coating to be safely introduced commercially at scale. And by introducing these high energy materials at high voltage, we can drive 35% energy density improvement at the battery level, and hence drive 30% cost savings, which is a significant improvement. In terms of how the technology works, there's 5 improvement mechanisms that we provide to and drivers of benefit that we provide to cathode material. One is we prevent the dissolution of active metal that then leave the cathode material, migrate to the anode, and accelerate aging. We prevent the surface phase degradation of the cathode material, so crystalline to rock salt transition, which is the picture that you see on the right-hand side. And we keep that boundary layer very well defined between the cathode material and the electrolyte over the life cycle. We also, in terms of power performance, we stabilize the solid electrolyte interface, and we lower the cell impedance thanks to the higher conductivity of the graphene. The third large driver, and that's the 5th mechanism to improve performance of battery materials thanks to our graphene coating, is the ability to improve the process manufacturability of the cathode as an electrode, because we have the ability to remove carbon black from the electrode, which improves the calendaring and the ability to control the thickness of the electrode. And also our coating improves the wettability of the electrolyte, which drives benefit in terms of formation time. In addition to superior performance improvement on the product side, a core feature of our technology, it's its ability to directly integrate in the existing supply chain and to scale up with through a modular deployment of our manufacturing process. So in terms of key feature, our technology is fully drop-in because our technology takes as an input a commercial cathode powder that's made by chemical companies such as BASF or Umicore, for example. And what comes out of our proprietary coating process is a coated cathode powder with our graphene precursor that's exactly of the same form factor as what comes in and can be used directly as an input to the mixing step of battery manufacturing without having to retrofit or change in any way, shape, or form the manufacturing process. So that makes our technology fully drop-in. In addition, our technology is highly scalable at low cost because in all of steps, whether it is the graphene precursor or the coating process, it's based on liquid process that operates at mild temperature and pressure and that only relies on off-the-shelf commercial equipment. In addition, our graphene coating is a platform technology that's applicable on multiple lithium-ion chemistry, NCA, NMC, LMO, and as I was mentioning, LNO is where we're focusing right now. And it's also compatible with other innovations that are happening in the industry, such as silicon anodes, solid-state batteries, for example. A little more detail about why our conformal coating is a low-cost coating. It's not a CVD-based coating. It's few-layered graphene of very low aspect ratio, and essentially we combine our small graphene flakes with a polymer binder, and with this, by doing that, we allow to reconstruct the coating at the surface of essentially any substrate. So right now we're focusing on cathode materials. But there's also applications on high power anodes, on separators for batteries, and beyond batteries, our technology is also creating value, and we have products that we are less actively commercializing right now on conductive inks and or on fuel cell coatings, for example. Compared to other advanced cathode technologies, I think the way our technology differentiates, it's along two dimensions. So first, because we coat with a graphene precursor, we combine the protection and conductivity, and we bring that product value in a way that other technologies don't. So that's the vertical dimension on this axis. The second differentiating factor is, as I mentioned earlier, we're not a CVD or ALD technology, so we are a one-pass, three-step process, which makes our technology scalable at low cost. Actually, our models right now show that at scale we add 1 to 2% to the cell cost while saving 30 to 35% cost by increasing energy density. In terms of business model, we are still early in our commercialization stage because the company was founded in 2018. But we have a broad range of approaches that we are currently testing with lithium-ion player, and that ranges from licensing to coding services to all the way to being a material supplier. We have strong engagement across the value chain, and we have 10 working agreements as of now, including 3 paid agreements with cathode manufacturer, battery cell suppliers, and or OEMs. We actually have a few engagement with Japanese companies, and we are looking for more, for sure. Our journey to date, so through the chain reaction innovation, we have developed a pilot line. We have validated technology on single layer pouch cells. We have demonstrated over 1,000 cycles, and we've validated a number of industry partnerships. We have just finished raising our seed round of $2.2 million, which will allow us to automate our pilot line and get to this ton per year scale that Chip was talking about for Nanograph, and that will be over the course that will be early next year. We still have $300,000 open in this round, so if you're interested in that opportunity and or in commercial partnerships, I'd be happy to answer any questions and follow up with you.
Okay, thank you, Damien. So yes, we have a couple questions coming in here, and I'm going to start off with a similar question that I asked chip. What key characteristics are you looking for in commercialization partners? And obviously you can touch base on Japan a little bit more if you'd like, since obviously Nanograph is a little bit more mature of a company. So.
Yeah. So we think about our scale up and our commercialization. There's going to be 3 pillars that we need to develop. One is the graphene precursor scale up. 2 is the coding process, and 3rd is the integration of this of our coded product in battery cells. We have a very good handle on the product itself, so on the graphene and the coding process. However, we are definitely looking for expertise in applying our product to commercial batteries. That's definitely one area that we are missing, that we are looking for partners to bring that expertise. And the second one, I would say, is to also identify which cathode material is the best fit for us to apply our coding to. So we're looking for partnership both on battery cell and on cathode material manufacturing to try to find that perfect match that allows to deliver the most value.
Very good. And what is your expected growth over the next few years? And and the level of dependency on the global supply chain as well. So.
Yeah, so expected growth. So the pilot line will be up and running early next year. So we'll be at ton scale at this point, which will allow us to start engaging in the commercial cell validation with battery manufacturer, and we expect to be commercial in early 2024, because that's one of the core features of our technology is we are enhancing technology. We don't need to reinvent everything from scratch. So we can enhance commercial NMC 532s, for example, for specific applications. NMC 811 is a big area of focus for us right now. So we are really that fully drop-in solution that can fully integrate with the industry. Did I answer all the question, or did I miss half of it?
Just the dependency on the global supply chain.
So the dependency on the global supply chain. So definitely we have an interest in engaging in Asia, particularly when we talk about specialty applications such as drones, e-bikes, and so on and so forth. On the global supply chain, I think there is one core feature of our technology that we didn't touch upon during this presentation, is that we're also an enabler of battery materials recycling, thanks to our ability to prevent active metal dissolution. So when you recycle cathode materials, copper, it becomes a huge problem. And because our coating retains the active metals within the cathode material, we enable we enable the use of recycled cathode materials, because we can keep the copper within the particle instead of contaminating the whole battery. So we kind of alleviate some of the risks on the global supply chain on the metals and mining side.
Hey, that's good. You just answered my next question on recycling. So I have another question here. What is the ideal application for Alexion's solutions? Power tools, robotics, industrial machinery, or automotive, or maybe all of the above?
Yeah, I think it's all of the above. I think one core differentiator of our technology is the fact that we bring this comprehensive performance improvement both in energy density and power. So we're going to go for specialty applications first, because that's where we deliver most value both on power, high temperature, or low temperature, and energy density at the same time. So we have this perfect storm in these applications, and that will allow us to start driving economies of scale and drive down the cost of technology before entering the electric vehicle market.
Very good. Do you have any other final comments you'd like to make before we end this question and answer?
No, I think that's it on my end.
Okay. Merci beaucoup, Damien. Thank you so much. Excellent presentation. And now we're going to go ahead and switch it over to our next speaker from Ateos, Rajan Kumar. Ateos is a Techstars-backed startup developing a platform technology for manufacturing highly customizable and flexible batteries that can be integrated into electronics manufacturing. This technology can be enabled in flexible electronics such as smart textiles, soft robotics, IoT devices, and medical fitness-based wearable patches. Rajan Kumar is CEO of Ateos with a bachelor's degree in nanoengineering from State University of New York, Albany, and a master's and PhD in the same discipline from the University of California, San Diego. Rajan was described by his nominator as one of his few engineers that can translate research into commercial products and use innovation to change the way existing industries operate. His goal is to grow his company around innovations that will increase the life and charging speed of batteries while also lowering the cost. So Raj, I'll go ahead and turn it over to you now. And unmute yourself.
Yep, thank you. Yeah, thank you. Thank you, Kevin, for that introduction. Yes, my name is Dr. Rajan Kumar. I am the CEO and founder of Ateos. So wait, see. Okay, do we see slides? Just clarify.
Yes, yeah, it's back up now.
Yes. My name is Dr. Rajan Kumar. I am the CEO and founder of Ateos. We are reshaping batteries through rapid manufacturing and merging it with advanced materials. And so my background, as I mentioned, in nanoengineering comes from 10 years experience in the semiconductor industry. And what I've noticed is what has driven innovation that has really empowered Moore's law isn't really derived simply in innovation in materials. It was constant innovation in the manufacturing. And while I see, the importance in advancing materials and batteries, we feel that batteries are primed for this paradigm shift, where we're chasing each decade to find these new materials to change batteries, but we're looking at the missed opportunity to improve battery manufacturing. And more specifically, what we find is that this tape casting process that is used to make the key components to the electrodes is a very archaic process. This is where we're mixing these powders into these slurries using a tape casting technology that was developed in the 80s to make VHS tapes. And the challenge with the semiconductor industry is it can have these very advanced features, but it's not scalable for the roll-to-roll production that we need to meet the demand from IoT to electrification. So here at Ateos, we want to move away from the dependency on this legacy thermal drying, where this is an approach that is very slow, very toxic with all these solvents, very capital intensive, but ultimately very limited in battery design, where because this process is so slow, we're just kind of limited to this very homogeneous design of battery electrodes. At Ateos, we envision a new way of manufacturing and designing batteries, where we use a light-based technology that is 10 times faster, it's environmentally friendly, but more importantly, will enable more freedom design, where we can build this single electrode in more complex layers with an instant flash of light to get better design in terms of energy and power, and then leveraging those new advancements in materials. We see this as approach, we've already proven that this process is chemistry agnostic, meaning that we can apply this to versatile materials from existing cathodes and anodes that are being used today and the ones that are going to emerge in the next coming decades. What we're really exciting is that we see this technology also expanding into other applications and form factors of batteries, where it'll have a dramatic impact in IoT, wearable batteries, really small factor, to power tools, and eventually the vision of doing electrification and grid storage. That being said, this is where we're really focused on building this ultimate solution where for decades, OEMs who are manufacturing these sensors and wearables are limited by these very rigid, bulky batteries. With our solution and with advanced materials, we can really build a flexible solution that is built around the product. And just to give you an example, kind of what are the key challenges these OEMs are facing is where, a typical OEM that is building this cutting edge diabetic monitor to help diabetic patients monitor their device, they're looking for three key things. They want to obviously miniature it with more energy density. The other key thing is that 90% of these wearables and IoTs rely on high pulsing for wireless communications. And the third challenge is, we're envisioning this ubiquity of computing, put sensors everywhere, but we're talking about trillions of sensors. If we look at how electronics are manufactured, all the components, the logic chips are reflow soldered in a very robotic fashion, but the batteries is this big bottleneck where they're inserted into these bulky clips. And it's a huge bottleneck for customers that want to do 50 or even 100 millions of units per year. And so this is where we're leveraging our technology to build the solution. This is where we're building a primary flexible ultra-thin battery demonstrating a high energy density. We've already proven a minimal voltage drop during this BLE pulsing with a common Nordic chip. And then we're already proving out a surface mountability approach with traditional solder paste. This is where we compare in terms of existing thin film surface mountable batteries. We have already proven that we have the highest energy density. We've proven out field testing with a BL pulse that is superior compared to existing coin cells and thin film chemistries. The surface mountability is a huge add-on for customers who want to scale, and we can do this with our manufacturing and our partners to do it at near price parity. And as you know, as I mentioned before, we're really excited to expand this chemistry into rechargeables as well. This is where we've leveraged the technology to build a rechargeable, ultra-thin, flexible battery. You can see here, this is one of, I don't know if you can see my picture. This is a prototype demonstrated here, a flexible battery we've designed for a major OEM for wearable devices. This would go into a headband or for a soldier. Here is a interactive video showing that flexing. So we're basically bending this battery in half, and there's literally no change in the voltage. And we can do this with multiple chemistry types. We've already proven with NMC 532 and NMC 11. And this is where we've compared the cycling testing of a stationary battery and a flexible battery. We're only seeing a 3% loss in performance after multiple iterations, already proving out 100 cycles. We're really excited about this product. We're improving the energy density. We're now leading among all the thin film rechargeable batteries. We have only tested cycles life 100 and are at a very low peak current of C over 5 based on our current customers. But as I mentioned before, we're chemistry agnostic. We are confident that these NMC-based chemistries or lithium iron phosphates will prove out to that 100, more than 1,000 cycles and the higher C rates. And I think the key thing is, that was kind of the first discussion, the challenge for batteries, scaling up technology. I've been in the semiconductor industry, and it was difficult for the industry to expand, to make any key innovations without these key infrastructures and partners. This is where, as soon as we, closed our seed round about 1.25 last fall, we incubated at the Battery Innovation Center. This is a $15 million battery pilot. We're able to do pilot production of our both products, move testing really quickly, and solve problems as we move forward. And so I think our focus today, we really want to reach out to appreciate the opportunity to present in front of JETRO and its partners. We're looking for two things. One is potential OEMs that are looking for better battery solutions to power their sensors. And what we're moving forward is we already have customers that want to do 1 million to 300 million to 10 million units per year in the next 1 to 2 years. What we're looking in our business model is that we're really good at manufacturing these key electrodes and processing them. We're looking for a partner in JETRO to help us with the assembly and scaling up this technology. We have a very strong team, combination of both, deep tech and also in the battery space. Myself, 10 years experience in semiconductors and print electronics. Also fame of developing the world's first printed stretchable battery. Carlos Munoz, our CEO, has been with us since the beginning, helping us commercializing and closing this recent round. We have a strong team of advisors who have scars and tough scars from building other battery companies. Al Vanderberg was CFO of Enerdell, and then Dr. Jeff Nelson has been CTO of multiple battery companies, supported with a strong team of business advisors, David Mendez and Sheila Nichols. So thank you for your time. Happy for any questions and so forth.
Thank you so much, Raj. Excellent presentation. I'm going to kind of start off again with one of the questions that I received this in the registration. What are some of the characteristics, that you're looking for in commercialization partners. I don't know if you want to go into any more detail. I know you just kind of mentioned it in your last slide there, but if you want to go into more detail for that. So.
Yeah, no problem. So we already have 2 active customers. We've already done a pilot run. They want to do to a production of roughly 10,000. We're looking at 1 million units to 10 million units per year. The bottleneck, as we, in the US, there's not much assembly support. So what we're looking for possible partnership of, we'll manufacture the electrodes. We're looking for a partner that can help with the assembly. Obviously, if there's interest in helping us accelerate the development of this electrode processing for to drones, EVs, and even expanding to solid state, where we're saying the future of solid state needs to scale up to over 20 meters per minute. And we believe this process will make it happen.
Okay, another question: How does Ateos thin film product compare with Amperex technology?
Which one? I didn't hear that.
Amperex.
Amperex. I'm not familiar with that. I'm not sure if they sell an ultra thin. So.
Yeah, I'm not exactly familiar with them either. So sorry. Maybe you can give kind of an outlook on how you're expected to grow in the next few years, and maybe your kind of dependency on the global supply chain.
Yeah. So for the first question in scaling, yeah, I think that's always a challenge with any battery companies, is how to scale up that manufacturing. This is where we're just focusing on a very low-hanging fruit, very simple battery tech, validate the process, and then eventually pursue, drones and EVs and expanding that far. For the supply chain, yeah, I think there's a challenge where, we're looking at approaches to upcycle materials. We're working with partners where, in the steel manufacturing, they produce massive amounts of tons of waste graphite in their process of making steel. We're looking to upcycle that and incorporate that as carbon additives in the anode and so forth to reduce cost and, just be more efficient.
And can your batteries be recycled?
I mean, they're still lithium-based. We're not focusing on that. Obviously, we'd be dependent on whoever develops the next solution.
Okay. And you've talked a little bit about challenges to scaling your technology. If you want to maybe elaborate that just a little bit more here. That was another question.
Yeah. So from our process, the manufacturing electrodes is 10 times faster. The output is going to be, so we believe that's a process that can move much faster than a typical gigacoder. It's much faster, a fifth of the capital, and ultimately better design. So we think we can scale the electrode manufacturing. The big bottleneck is always the assembly and formation as kind of the back end of the line of the battery assembly process.
When I see your technology, I'm really looking more at like the kind of the wearables industry and more of the smart textile, smaller things. So you've mentioned like EV. How do you get this type of flexible electronic battery into the EV and down the road?
Yeah.
Maybe what's the timeline for that?
Yeah. So I mean, we're already seeing some significant values where the challenge is, I think one people are looking at is doing higher loading weights, depositing more material, thicker coatings. Like Tesla has been talking about this dry electrode process, making 1 millimeter thick kind of cathodes and anodes to get higher, just more energy in that cell. The one challenges we've seen is that as you get thicker, it's much harder to process. They get more brittle. By enabling our additives to make them more flexible, it's also with the polymers that we're using with our process, enable the battery to be more flexible. That's applicable to the higher loading weights needed for drones and EVs, where we're already showing that if we do a traditional chemistry, traditional legacy electrode, it's harder to get higher loading weights over 50 milligrams per centimeter. It's very brittle, very hard to calendar. Obviously, you can make some on it, but we're seeing no issues with that right now with our process, and including with advanced materials.
And is the operating environment of these batteries comparable to standard batteries, like i.e. temperature range? And I'm going to launch a poll here too while we're talking.
Yeah, but at this moment, we're not advancing anything in terms of the performance. We're just validating the superior manufacturing, a little bit better performance design on flexibility and some current profiles. Eventually, we'll look at those when we enable more value prop with the manufacturing process.
Sure. Well, thank you so much. We'd like to give you a chance to leave some final comments if you'd like.
Yeah, I think this is, I think the story, I think right now we're seeing with semiconductors, right? There's a huge bottleneck in chips. I think the same thing is going to happen with batteries. There's history of semiconductor working together to solve big technical challenges, move the industry forward. I'm really excited for the battery industry to take that kind of attitude in solving big industry challenges like manufacturing, where it's going to take time to develop very high capital. Instead of each company trying to do it alone, we share it together and bring those innovations forward.
Thank you so much. We look forward to working with you in the future, Raj.
Yep. Thank you, guys. Appreciate your time.
Okay. Thank you so much. Now we're going to move to our final speaker, Salil Saman of Brightvolt. With the state-of-the-art research and development center in Indiana, also the Battery Innovation Center, and corporate headquarters in Redmond, Washington, Brightvolt is bringing superior battery products to market with a global reach. Their rechargeable solid-state batteries can power all types of applications, including hybrid and electric vehicles, consumer electronics such as smartphones, laptops, e-readers, and drones, medical and wearable devices, and other information technology products. Salil Saman is Vice President of Business Development at Brightvolt. Prior to joining Brightvolt, Salil was Vice President of BD at Natron Energy, where he led corporate business development activities for their sodium-ion battery technology in data center and telecom, UPS, electric forklift, and stationary grid storage markets. Saman carries more than 20 years of experience across multiple battery technologies, including Zinc 5, BASF, and Robert Bosch battery systems. He holds a Master's of Science degree in Electrical Engineering from the University of Massachusetts and an MBA in Technology Management from the University of Colorado. So Salil, good to see you. Thank you for your patience.
Right, excellent.
So,
thank you so much for the introduction, Kevin. Can everyone see my presentation?
Yes, looks good. So I'll go ahead and turn it over to you.
All right, wonderful. Well, I understand people might be joining us today from different parts of the world. So let me start by saying a very good morning, good afternoon, and a good evening, depending on where you are. My screen keeps switching here. Let's see, are we still in full screen mode? Quick check.
No, it's not in full screen.
Okay.
There we go.
Now?
Yes.
All right, excellent. So I'm going to switch gears a little bit. We heard some excellent talks this afternoon, or this morning, I should say, from previous speakers talking about anodes and cathodes and unique cell designs. I'm going to spend a little bit of time talking about our proprietary technology, what we call a polymer matrix electrolyte, or in short, PME, essentially looking at replacing a separator and electrolyte in a lithium-ion cell. So let's start with a real quick corporate overview in terms of who we are. Brightvolt is headquartered in Redmond, Washington, just outside of Seattle, with R&D based at the Battery Innovation Center in Newberry, Indiana. We are backed by a syndicate of several venture capitalist firms, or VCs, the most prominent one being New Science Ventures out of New York, Bramer Energy, and a few others. And the company was rebranded to Brightvolt in 2014, prior to which we were known as SolidCore, and we were focused exclusively, heavily on thin film primary batteries, so disposable kind, non-rechargeable technology, focusing on multiple applications such as IoT devices, medical trackers, fintech markets, and so on. The company has a rich history in the primary cell technology. We have sold over 15 million of those batteries, shipped around 17 or 18 countries in the world out of our own manufacturing facility in Florida. And now what we are focusing on is development of rechargeable PME technology, essentially a solid state battery that can offer very high energy density, long life, and excellent safety at a low cost, with initial target markets being consumer electronics, or in short CE, as well as automotive EV applications. So let's talk a little bit about our technology in more detail. If you look at any conventional lithium-ion battery today, in a very broad sense, it comprises of 4 basic components. As we all know, there is an anode and a cathode, which are your 2 positive and negative electrodes. And then you have a liquid electrolyte that shuttles the ions back and forth between these 2 electrodes, and then a separator membrane, which basically offers electrical insulation between the 2 electrodes while allowing those ions to pass back and forth. And so the approach we took here with our PME technology at Brightvolt was we asked ourselves a question, well, what if you could somehow combine two of those battery components in the incumbent lithium-ion technology, namely the separator and the electrolyte, to essentially make our battery a 3-component system versus a 4-component system? And so that's really the backbone of what the polymer matrix electrolyte technology is comprised of. And so if you look at the individual constituents of electrolyte and separator, as we all know, the liquid electrolyte is usually a mix of one or more lithium-ion conducting salts that are dissolved in an organic solvent. And then the separator is usually a PP type membrane. And so in a nutshell, what the polymer matrix electrolyte, or the PME, comprises of is a backbone polymer combined together with one or more lithium-ion conducting salts and a plasticizer or solvent, all in a single homogeneous and a uniform state. And so when we start preparing, and I'll speak a little bit more about this on the next slide, but when we start preparing our PME, it's in the form of a solution or a gel with a viscosity that's very similar to what you would have in a conventional lithium-ion slurry. And so we start with mixing our PME in the slurry in place of the conventional binder that you might use. So there's no need for an additional binder. And after you mix that and prepare your slurry, you would proceed to prep your electrodes just the way you normally would in terms of coating them onto a substrate and then going through drying and calendering and so on. And at the end of that step, we put one more layer of our PME on top and then allow that PME solution to fully dry or solidify. And so the benefit of doing that is once the electrodes are prepared through that process, you really have just 2 electrodes, your anode and your cathode, that you can slap together, essentially making a battery. So it's something as simple as slapping 2 slices of bread and making a sandwich. So let's jump into a bit more detail on how that's done. So what you're seeing on this slide here is a conventional lithium-ion cell design architecture on the left-hand side. So you have a graphite, superior graphite-based anode with liquid electrolyte. You have a NMC type cathode, and then you have a separator, and then there's liquid electrolyte throughout. Now, what we do here, as I was mentioning earlier, is with our PME solution, we start by incorporating that PME directly into the anode and cathode, and that's is used as a binder, and then we proceed to put one more layer of that PME on top of the electrode. The benefit of doing that is multifold. One of the most obvious ones is that, as we all know, the electrodes in a battery carry a certain level of porosity. And the idea with conventional lithium-ion batteries is that when you pour the liquid electrolyte goes in and fills up those cavities or empty pores in the electrode structure, and that's where you form your ion conducting paths. Now, the benefit of putting an overcoat of the PME on top is, as part of the drying or solidifying process, some of that PME layer that sits on top of the electrode actually interpenetrates into the open pores or the open cavities of that electrode itself, thereby creating multiple conducting paths, as a result of which we get really low interface resistances. Another benefit, of course, is in a conventional liquid-based lithium-ion battery, as we know, the open pores are for that exact reason, is where you want to put the liquid electrolyte and create those conductive paths. With our technology, we don't have a need for having that high level of porosity or low density, because we don't need to fill any liquid electrolyte since the PME solution is already into the slurry to begin with. And so that allows us to truly densify our electrodes, which results in a good bump in energy density. And also the fact that you're creating some, opening up a lot of volume in the cell by actually eliminating that liquid electrolyte. Also, if you were to cross-section one of the battery electrodes and look at the so-called PME only layer that sits on top, it's an extremely thin layer that basically serves the function of a separator, and it's already in the sub 10 micron range. And then, of course, moving from this more of a standard conventional cell design, going into some more novel materials such as lithium metal anodes or silicon graphite anodes, then gives you a further bump in energy density. And so when you look at value proposition of a technology such as ours, it's really fourfold. One is that the technology can offer a very high level of safety, or extremely tolerant to electrical, mechanical, and thermal abuse. And that's in large part because there is no free-flowing solvent or liquid based in the cell. The technology can also offer very high energy density, and that again comes from three areas. One is densification of electrodes. The other one is compatibility or use of high voltage cathodes, and then compatibility or use of high capacity anodes such as lithium metal or silicon-based anodes as well. The technology is very low in cost, so we like to look at cost from two perspectives. One is at a single cell level. So if you just take a look at bill of materials and look at replacing that liquid electrolyte and the separator membrane with our PME, that gives us savings in the ballpark of 12 to 15%. But then given the extreme abuse tolerance of the technology, when you look at things at a pack level, I think it also enables ways to simplify the battery management system and the thermal packaging, resulting in another 5 to 7% savings at the pack level. And then last but not least, we understand for the markets that we're going after, you can't really compromise in terms of temperature performance. And so the PME is demonstrated to work all the way down to -30°C up to at least 100°C. And I'll be sharing some data here shortly. And then in some of our next generation products, we are actually looking at pushing that envelope even farther, especially on the high temperature side. So if you look at essentially a PME to replace or do the function of a separator and electrolyte, there are many different properties that you would be looking at. I'm going to share just one or two critical ones in today's talk. So the first and foremost is ionic conductivity. And so what you're seeing here is ionic conductivity data. It's a logarithmic axis on the vertical of the y-axis, plotted against a wide range of temperature, again going from -30 up to 100°C. And what you'll notice here is, in case of the PME, it delivers a minimum of at least 1 millisiemens per centimeter of ionic conductivity all the way down to -30, which I think really differentiates this from some of the other competitive polymer electrolyte solutions that we have seen in the market today. Another aspect of the product is, of course, looking at its electrochemical stability or voltage stability. And so what I'm showing here is a cyclic voltammetry scan. And what you can see is the PME has very low reaction rates or oxidation reduction reactions going on, electrochemically very stable up to 4.3 volts, which is where we routinely and commonly charge our batteries to, probably even up to 4.5 volts. So compatible with high voltage with NMC-based cathode materials as well. Another important factor that you'd probably care for is the mechanical strength of the film, or the PME, and that's important because it helps prevent puncturing or dendrites from shorting cells, especially when you think of use of lithium metal anodes. And so, as you can see on this slide here, the PME is very mechanically robust, very uniform, and it can easily bend and flex into different shapes and form factors, which is maybe not so much critical for the automotive market, but it certainly is for consumer electronics when you think of applications such as fitness trackers or smart glasses or headbands and so on, like one of the previous speakers had suggested. So what I'm going to show here is I'm going to try to play a short video. Let's see if technology cooperates. So yeah, not a scientific test by any means, but it just goes to show that the PME is inherently very strong mechanically. A quick talk of mention of our patents. So given our as I said, experience and work in the primary thin film solid state battery market for the past few years. We have a fairly extensive patent portfolio, extensive patent coverage worldwide on the primary front, and we are now starting to build our patent portfolio equally well on the rechargeable side as well. And so, why am I here today? We very much believe in building right partnerships for the markets that we are focusing on. We believe our technology is really unique in the sense that it can offer several favorable performance attributes for consumer electronics and automotive EV markets, especially in the areas of low cost, high safety, and improvements in energy density. What we are looking for are strategic partners and collaborations with Japanese entities. And for us, that could come in multiple ways. One could be joint development agreements to start putting this technology into first correct go-to-market products for CE and EV applications. We already have partnerships with funded partnerships, I should say, with multiple Fortune 50 automotive car companies and also a Fortune 200, global Fortune 200 utility company in the world. A partnership with a battery and battery raw material supplier as well, and we're looking to build upon those with some of the Japanese OEMs here. I should also probably mention we are currently fundraising, so we have a $20 million Series B fundraising round with a lead investor identified, and we are looking for some new co-investors to follow on to close that round. So if there's any interest in those discussions, I'd be happy to chat about that as well. And so really to summarize what we talked about today, I'm not going to read through this slide in entire detail, but when you look at solid state, there's no doubt the shift to solid state is inevitable, especially in the automotive EV space. But when you look at some of the technologies coming in the market today, a lot of those are coming out of incubation, early stage incubation in universities and national labs. And I think what differentiates Brightvolt technology is the fact that we have already commercially sold millions of cells in the primary market, and fundamentally we are taking the similar or same approach to our rechargeable PME development as well. And so the company very much understands what it takes to make something in a very high volume and make it extremely cost competitive and at scale. And so with that, I'd be happy to answer any questions that you may have.
Thank you for your excellent presentation, Salil. I've got a couple technical questions here. What kind of polymer do you use as a backbone?
So it's a combination of two polymers. One of them is a proprietary polymer that we make in-house, and another one is a off-the-shelf polymer that we blend with our own.
Okay, thank you. And how does Brightvolt compare with TDK's Seracharge? Sorry, I'm trying to read through this question. Seracharge solid-state batteries in EIA 1812K size?
I'm not very familiar with that particular technology, Kevin.
Recharging cycles?
If somebody could follow up with me offline, I'd be happy to take a look and then get back to them.
Sure, okay. And actually, I'll go ahead and launch the poll here. That way, that person can, if that person can reach out here, we'll make sure to connect you afterwards.
Absolutely.
And then here, just another question. I know you've kind of talked about commercialization. You know, I think I met you at AABC Tokyo back in 2019, but, you know, maybe if you want to just elaborate a little bit more on maybe what you were looking for in Japan, if you didn't say everything that you wanted to. So.
Yep, absolutely. Thanks, Kevin. Yep, so at Brightvolt, we very much believe in an ecosystem to bring our technology to the market. And so for us, the partnership could come from 2 or 3 key areas. One is from an OEM side, where we very much would value a strategic partnership with an OEM who would be interested in putting our technology into their products. And then also on the raw materials and cell design, or I should say cell manufacturing side, companies such as Panasonic, of course, but there are many others in Japan that come to mind. Those would be, I think, the right strategic partners that we'd be looking for.
And you know, you've been around for a little bit, kind of like Nanograph. What is your expected growth over the next couple of years here, and your level of dependency on the global supply chain?
That's an excellent question. So as I mentioned as a part of my presentation, Kevin, we are going after two key markets. We see bringing our technology first on a commercial scale in the consumer electronics or the CE market that we are targeting in the mid to second half of 2023. I've personally been in the automotive market for over 20 years, and I know how slow and how hard it is to get a new technology qualified in that market. And we are fortunate that our investors appreciate that as well. So we are taking a longer term view to the automotive market. We believe that this technology would hit the automotive market somewhere 2025, 2026 timeframe. Did I answer all of your questions there?
Level of dependency on the global supply chain. I don't know if there's anything you want to add.
Yes. So there's nothing really proprietary in terms of the active materials that we use. And so we are somewhat dependent on the same fluctuations on metals, and we use basically off-the-shelf active materials in our anodes as well as our cathodes. It's really about mixing our PME together with some of those materials and then putting them together into our cells.
And do you have any material recycling plan in place, if any, if necessary?
Not at the moment. So as we heard from the previous speaker, we'll probably look for the right partners in that area when we are at a meaningful volume to look into recycling as well.
Sure. Well, thank you so much for your presentation. I'd like to let you give any final comments here, if you'd like to.
No, I think just want to say a quick word of thanks again to JETRO. I think you are doing an excellent job here. I very much appreciate the opportunity to speak today.
Thank you so much, and we'll look forward to speaking with you again soon. I enjoy all your LinkedIn photos of flying a helicopter, and I think you're a pilot, correct?
I'm a private pilot. Yeah, I fly airplanes, not helicopters, but you're close.
Okay, for some reason I saw you in a helicopter. I thought you were flying.
That is fine.
Okay, thank you so much, and I'm going to launch one last poll here. This is just a kind of overall webinar poll, and I'd like to thank everyone for sticking to the end here. A good amount of you stayed. And thank you for our excellent presentations and comments today from our speakers. We're looking forward to coordinating upcoming webinars with timely industry topics, such as carbon neutral technologies, smart cities, Industry 4.0, and more. So stay tuned for announcements on our Jconnect landing page on our JETRO USA website. So we look forward again to seeing you at some upcoming webinars, and thank you again for attending. Have a great day.